Good morning. What can I do to help you? Everything? Okay, let's start with your personal life. You want to tell me anything? No. All right. Do we want to just work through this list? You want to start asking questions? What do you need? Work through the list? Okay, let's work through the list. And we'll just, you guys need to tell me if I'm going astray or if I'm hitting the nail on the head or whatever, right? Okay, so conservation of momentum. What are the possible questions I could ask you about conservation of momentum? Well, I'm not going to ask you what. Have I ever asked for a definition on any exam anywhere? No. What's my assumption going into the exam? That you know those definitions, okay? So I'm not going to what is it? So there are two kinds of collision. Elastic and inelastic. So conservation of momentum could be either or, right? You get one conservation of momentum question. It could be inelastic or it could be elastic. So be prepared to be able to handle both kinds of problem. The main difference between inelastic and elastic is that elastic, you have a special equation to help you. I gave you a magical mystery elastic only equation. With inelastic, you're doing a sandwich, right? Sometimes you need to do conservation of energy beforehand or after, right? But you're applying conservation of momentum right in the middle where the two things are interacting. Okay, in that instant they're colliding with each other or sticking together or something like that. So for conservation of momentum, possibilities include, right, inelastic or elastic, right? Just be prepared to be able to do those problems. You'll get one. You're not going to get both. You get one of those, right? So be ready for it. Impulse. And we can circle back on some of these if you want more detail, but let's just talk about all the possibilities. What could I ask when it comes to impulse? What was impulse involved with? Force and time, wasn't it? Okay. So being able to calculate the impulse itself, which is a change in momentum, right? But that also being equal to force times time. So there's various possibilities in there, aren't there? For a given impulse and time, find the force. Or, how much time is required to get a certain force out of a certain change in momentum. It could be so here's the thing that I watch students mess up with impulse every single time. And it doesn't matter how clearly I state this, keep track of the directions of things. Momentum's a vector. If something is moving to the right and it bounces off, if you said moving to the right was positive, what does the final velocity sign have to be? Negative. If something falls and bounces off the ground and you say it falls at 10 meters per second, what do you have to say the rebound direction is? Negative, right? You can swap that. You can say, moving up is positive. Well, then if something's moving down, it has to be negative, right? You've got to mind your directions. That's usually, after that, being able to solve for force or time or whatever is just a matter of division or multiplication, right? It's the signs on the velocities that students will screw up on. And, fair warning, right? You mess up a sign on one of those, that's easily a -1, if not a -2, right? Because it's fundamental physics has not been checked in terms of those vectors. Rotational kinematics. It's a toolbox, isn't it? So we did the toolbox. I actually don't remember. It could be also like rolling motion, where the velocity of the center of mass is equal to r omega. And then don't forget that there's Google Translate equations in there that get you back and forth from v to omega, of a to alpha, right? So being able to deal with objects speeding up and slowing down. I mean, in the old days, we used to use record players, but nobody knows a record player. Although vinyl's coming back, isn't it? Turntables, merry-go-rounds, Lazy Susans, washing machine, drum, a dryer, like anything that rotates and then would speed up and slow down. And then in kinematics, like you're looking for alpha, you're looking for time, how far something rotates. Right? Either in radians or in revolutions. There can be a lot of mix-up on like the units. Remember, what are the standard units for theta? Radians, right? So if they tell you 4 revolutions, what do you have to do? Convert that to radians, right? What are the standard units for omega? A radian per second. It's often given in revolutions per minute. Again, that must be converted. Alpha? Radians per second squared. So just having those standard units down on your cheat sheet can just, it offloads your brain from worrying about having to remember what they are, right? You can quickly glance over and go, oh yeah, that's what it is. Not much else to say about rotational kinematics. Again, I can ask you to solve for anything. Final speed, initial speed, how far it rotated, what its acceleration is. There's lots of variations on a theme there. And see your homework, see chapters 2 and 4, right? Like for possibilities for things. Although not exactly 2 and 4, because those are all linear things. Center of mass. Where did we do center of mass? In lab. Do you think, maybe, just maybe, it could be lab related, or at least lab adjacent? Can I ask you to find the center of mass of something, right? One mistake I've noticed on the center of mass problem is students often try to make it harder than it really is. Center of mass and static equilibrium are basically the same thing. It's 2 different ways of looking at the same situation. So I've watched some students on the center of mass problem use some of the torques equals 0, which does work. Like it will get you the right answer. There's just a lot more setup and a lot more place for it to go wrong. Center of mass, got that standard equation, get a 0, run with it. It's just, it tends to be a little bit less taxing on the brain to handle. So on the exam, remember I put the topic of the question. It's in italics at the end of the question. So you can look at it and go, wait, is this static equilibrium or is it center mass? Look at the topic, it'll tell you. Right? So just be mindful of that. Moment of inertia. This one's kind of, this is broad, and I wish I didn't say more because it would have totally given it away. And some of you are like, so? I mean, moment of inertia comes, it's in Newton's second law in rotational terms. So there's a way to find the moment of inertia of something. If you know the angular acceleration, how much torque is required to make that angular acceleration happen, okay? It also comes from the table, right? It could also be present in the rotational kinetic energy, 1/2 I omega squared. The point of this problem is to get you to figure out what the moment of inertia of something. I did something that past me actually turned out to be pretty smart, but recent past me freaked out until current me realized what I did. That's a long explanation for, I didn't put the table on the exam. Even though I promised you I'd put the table on the exam, I did not put the table on the exam because what I did is in the problems where you needed the table, I just gave you the moments of inertia from the table. Does that make sense? So instead of printing an extra piece of paper and all that kind of stuff, past me apparently decided I liked you or something and just gave you. Like if it said that the wheel is a solid cylinder, then I said I equals 1/2 mr squared, right? Like I just gave it to you in the problem. So please don't panic on Thursday when you don't see the table. I'll have a table, I can throw it up on the screen. I've got it all ready to go. But like, you shouldn't need the table. So if you've got a problem that's asking you to solve for the moment of inertia, chances are you don't need the table for that. But you might need the moment of inertia elsewhere in a different problem, right? So I wouldn't worry too much about that table, even though I said I was going to give it to you. I just gave you the moments of inertia that you would need. But you're going to calculate the moment of inertia. Now, this will hopefully make more sense tomorrow, because tomorrow we're doing the lab on moment of inertia. So it'll give you a little bit more context for what this kind of problem might be. And then conceptual question on rotational energy. What did we do together in class that was conceptual that had to do with rolling motion and energy? We rolled, right, the hoop and the disc down the slope. We reversed that. We talked about, things that are rolling at the same center of mass speed. The one with the higher moment of inertia will have more energy. So I'm going to ask you a conceptual question similar to those types of things, right? Okay. What has the most, it's not a ranking question. I never put ranking questions on. So if it were like, it could be like, which of the following has the most moment of inertia? Which one is the least or most energy, least energy? Which one gets to the bottom first? Which one rolls higher up the slope? Like there's lots of different ways to test your knowledge and understanding that something that's rolling has more energy than something that's just translating. If they're moving at the same V, the same center of mass speed, then the one that's rolling has more energy because there's a new kind of energy associated with that turning or rotating motion. So, conceptual questions admittedly are kind of hard to practice. They are specifically targeted at finding out how much you understand about the concept and not just can you manipulate an equation to find something. Physics is definitely more about the concepts and the proper applications of the equations, and the conceptual questions really target that, which is why most students hate them. And then static equilibrium, holy cow. Of all the problems on this list, which one are you going to attempt last? The static equilibrium. Wherever it ends up on your exam, do that one last, right? Why do that one last? Takes the longest. It's hard, right? Because you got to write down Newton's second law in the x and y directions, and you have to write down a torque equation about some axis that you get to pick, right? So I did my best to make the math part as easy as possible. I'm going to be looking for communicating a setup, proper equations, that kind of stuff, right? So, oh boy. Be able to pull that off. Okay, what's something you want to go over in more detail? Or maybe you have another question about the homework or anything like that. What do you need? What do we need to practice? What can I help you with? Conservation of momentum. Am I making up a problem? That would take too long. I gotta go find all my files and then do some crazy copy pastes and wait for the cloud to update and all that kind of stuff. I do have one that is seared into my memory because my students wanted to kill me after I put it on the exam.
Lay it on us.
Okay. I believe, I can't remember. It was either a penguin or a camel. We're going to go with penguin. A penguin starts at the top of an iceberg and slides down a frictionless portion of the iceberg until the penguin hits the flat area. On the flat area, there was friction, like a sandy surface, and the coefficient of friction was given. The penguin then went up a short ramp, after which it took off and soared through the air until it landed back on the flat portion, where it hit another friction area with a different coefficient of friction, and then ran into a snowbank that can be modeled as a spring being compressed. We haven't done springs yet, so I'll give you that. Okay. Find out how much the snowbank gets compressed when the penguin comes to a stop. We're not going to do this whole problem because on the surface it looks really hard, doesn't it? There's lots going on here, right? There's this whole like projectile motion section in the middle, right? The students that wanted to kill me, and literally they were standing outside my office after the exam, like 15 of them. They might as well have had like tar and feathers and pitchforks and torches, right? They're like, Mr. Balogh, that was unfair. And I was like, what? And they're like, that problem, it was unfair. And I was like, go home, calm down, and promise me you won't hate yourself next week during the test autopsy. And they're like, there's an easy way and a hard way to do this problem. The hard way, what those 15 or so students did, is they broke the problem up into every part. Finding like the velocity and position of the penguin at every point. Initial, final. Friction 1, friction 2. That's all you need. Work non-conservative equals the changes in energy. What's the total change in energy right here? Penguin's moving right here, goes up, slows down, right? Flies through the air, lands at exactly the same level. The change in energy is 0 for that section. The only things taking energy away from the system are the frictions. You start with a certain amount of potential energy, and all of that energy just gets consumed by the spring. You can literally do this problem in 3 lines. I'm still alive today because I knew how to hide. But those mad students, those tears of frustration and anger turned into tears of, oh my gosh, why didn't I just believe? I don't put this program on the exam anymore. This problem on the exam anymore. So that's not a good example. What would be a better example of like conservation of momentum? This one didn't even have a collision, although technically you could consider that a collision. What's hitting what? Give me 2 objects.
A Balogh in a car.
A Balogh in a car. Drew, are you trying to say something? Let's not go that violent.
Halo in a tree.
Thank you, Ella. Let's try to not hit people with things.
Myself in a concrete wall.
Now we're into self-harm. Okay.
Bouncy ball in the floor.
Bouncy ball on the floor. Okay. So let's do, actually, let's just erase this. Okay, so let's do a bouncy ball or any ball, doesn't matter. And we're gonna roll. So the ball's gonna be moving along, and then it's gonna go into a cup. Yeah, you've like played a little game of golf or something with a cup on the floor, right? You're rolling a ball or hitting a ball into a cup. Okay, and then afterwards, the cup and the ball will be moving together. Okay, find out how fast the ball was moving before it entered the cup. If the cup slides 10 centimeters after impact. Okay, so the ball's mass is 100 grams. And the mass of the cup is 50 grams. And the coefficient of friction between the floor and the cup is 0.1. I'm just making up numbers. I don't know if this is going to work. Okay, so we'll see if there's anything else that we need before that. Okay, so where do we start? Where's the sandwich? Where's the meat? Where's the 2 pieces of bread? The ball rolling is a piece of bread. Okay? So there's bread on this side. Bread. B-R-E-D. That's how you're supposed to spell it, right? No. And there's another piece of bread. Is that bothering you? Okay? So where's the meat? Or the veggies if you're vegetarian. Right? The very center is when they are coming into contact with each other in that collision, right? So I taught you to start where? In the middle, in the meat. Start with the meat. Okay? It'll tell you what to do with the bread. So, starting in the middle, we start with conservation of momentum, right? Inelastic or elastic collision? It's inelastic. How can you tell?
It's not mentioned as elastic.
Good, right? Or the fact that they stuck together. It's like a dead giveaway, okay? So, before, like the instant before the collision, we have to write down the momentum of everything. What has momentum before the collision? Not the cup? It's not moving, right? So it doesn't have any momentum. So initially, it's mass of ball, velocity of ball, right? And then afterwards, what has momentum? Ball and the cup. There's 2 different ways to do this, and they turn out to be identical in the end. You can treat the ball and the cup as separate objects. Or you can treat them as one total object. Like I said, it doesn't matter. If we treat them separately, we got ball v ball final, mass ball v ball final, plus mass cup v cup final. That's treating them separately, right? We could also write this as mass ball plus mass cup because they're stuck together. They're one mass, and then they have some speed. What do we know about V-ball final and V-cup final if they're stuck together? They're the same. So mathematically, it ends up being identical, right? If you have the same velocity, you'd factor it out, and then away you go. You'd end up with the masses adding together anyway, right? So I'll just continue on with my green version here, okay? All right. So what we want the velocity of the ball. That's the initial velocity of the ball right there, right? Do we know the mass of the ball? Yes. Do we know the ball in the cup? Do we know how fast the ball and cup are moving after the collision? No. Right? So here's what I want. This is in the way of me getting what I want. So what do? I set it equal to 0 and walk out. No, because then I'll just get v ball initial is 0. That doesn't work. I've got to figure out which piece of bread am I going to be working with? This one or this one? Not the front one. The back one, right? Something. So after it hits, it has speed v, doesn't it? Right? In the afterwards. But then it gets to a speed of 0, right? So there must be something I can do to figure out how fast it was going if I know that it went 10 centimeters with the coefficient of friction of 0.1. Your choices are kinematics, Newton's laws, or conservation of energy. Pick one, Griffin. Conservation of energy. Just do, if you're going to guess conservation of energy because it's the more straightforward one. So in blue, we're going to do this portion right here. Okay, conservation of energy. Work non-conservative, energy final minus energy initial. Is there any friction in the problem? Yes. So minus kinetic friction times the distance that kinetic friction acts. That's the work done by kinetic friction. How much energy does it have at the end? 0 kinetic? Is it moving? No. Is it rotating? No. Does it have gravitational potential energy there? No, especially if we put 0, right? Right there. So no energy to end with, right? Okay. All right. Initially, is it moving? Yes, 1/2 mv squared. Is it rotating? No. Does it have potential energy? No. It never changes its height, right? So this is the because omega is equal to 0, and this is because the height is equal to 0, right? All right. So what am I left with? I'm left with minus FD is equal to minus 1/2 mv squared. What do I do with the minus signs?
Cancel.
What do I do with F?
Turn to coefficient n.
Mu n. Don't forget the D. Solve this for V. 2 mu n d over m is equal to v squared. So the square root of that thing is equal to v. Where does that v go? Into there, right? It's a number, isn't it? Okay. I know mu. Oh, what's the normal force? Boy, I made that harder than it needed to be. mg. So this thing is the square root of 2 times mu g d. The m's cancel out. So that means this thing all right, and then solve that for v. I'm not going to mess with doing the numbers because that just takes time and I'll probably get it wrong anyway. But the point here is, for conservation of momentum, where do you start? Start in the middle of the sandwich. Okay? Let the middle of the sandwich inform you about the things that you need to go find. And then go find them using something else that's not conservation of momentum. If this were an elastic collision, your sandwich has 2 equations to it. The conservation of momentum statement, standard momentum initial equals momentum final, plus that magical equation I gave you that's only for elastic collisions. In those 2 equations, you'll have everything that you need in order to solve what's going on. Do I need to do an example of that? Yes? You were looking at me slightly blankly.
So we never actually solved it. We just found the formula.
I mean, for physicists, we did solve it. We know everything now, right? Except the one thing that we're looking for. We're looking for this. So solve this equation. VB is equal MB plus MC all over MB times the square root of 2 mu GD. And that's everything on the right-hand side of that's a number. I actually don't care what the number is. To a physicist, this is solved. For any mass, at any speed, for any friction, in any distance that it goes. In other words, I solved all the problems of this kind. Not just one of them. Okay. A ball slides down a frictionless hill. Ball number 1. And hits ball number 2. The mass of 1 is, you tell me. Mass of ball number 2. Find V1 final and V2 final. That's what we're after. We're given the height. What's the height? 4? Okay. Number 1, number 2. Hashtag 1, hashtag 2. Used to be the number, the pound sign used to be the number sign. Sorry, that's me being old. I believe we have everything we need. Okay. I'm telling you it's an elastic collision, so you don't have to wonder. Okay. So in an elastic collision, do the meat of the sandwich. Okay. So where's the collision? This thing rolls down, hits ball number 2, right? So the collision's right here, isn't it? So prior to the collision, what had momentum? M1, V1 initial. After the collision, what has momentum? Both of them, M1, V1 final plus M2, V2 final. What do we not know? These are our 2 unknowns, the final velocities of the balls. They weren't given. We're being asked to find what they are. One equation isn't enough to be able to do that. And so you whip out the other equation. V1 initial minus V2 initial equals V2 final minus V1 final. I believe that's the equation. That's me not looking at my notes. This is me looking at my notes. Nailed it. Why is that one fused in my brain? For somebody that has the memorization capacity of a goldfish? This has saved me so many times, right? From having to brute force the conservation of kinetic energy portion of this, which is where this comes from. It saved me so many times that I've just locked onto it because it's such a better way of doing it. Okay. So again, what are the unknown parts of this second magical equation? The 2 final velocities, right? So now I've got to put these 2 equations together. Out of character, I just put the numbers in at this point because symbolically this gets rough. So M1, 30, V1 initial equals 30. I'm just going to call it V1 because I know it's going to be the final, plus 55 V2. And over here I've got V1 initial, which I don't know. I got lots of unknowns. Minus 0 equals V2 minus V1. Okay, so I actually have 3 unknowns in my problem still, don't I? I don't know what V1 initial is. So now I have to kind of break off my normal elastic problem solving in the meat of the sandwich and go do some bread to see if I can't figure out how fast ball number 1 is going when it hits the other ball. So we're going to take a look at everything that happens on this side of the sandwich. And what are we going to use? Kinematics, Newton's laws, or energy? Energy. The answer is the square root of 2gh. We've seen that before, haven't we? How fast is something going when it, with no friction, slides down a slope or even rolls down a slope? Square root of 2gh. If there's no friction, meaning no static, no kinetic, it's not rolling, it's the square root of 2gh. How fast is something going when it falls through height h? Square root of 2gh. You can do the problem, the conservation of energy problem again. I'll do it real quick. There's no friction. The final is 1/2 mv squared. The initial is mgh. It's not moving up there. Has no kinetic energy. Has all potential energy. At the bottom, it has no potential energy, right? Because I put 0 down there. This is final. This is initial. If I solve this right here, I get the square root of 2gh. When there's no friction involved, the answer is square root of 2gh. So now I know what that velocity is. It's the number, whatever 2 times 9.8 times 4 is. That's 8 times 10-ish. All right, we'll do the real thing, because I can't do the square root of 80 in my head. 9.8, 8, square root. I got 8.885. So now that I know what that is, I can come over here, do 30 times 8.85 equals 30 V1 plus 55 V2. We need to go 30, 8.85, 265.5. And then all the rest of that. Over here, I've got 8.85 equals V2 minus V1. Which one do you want me to solve for, V2 or V1 first? Solve for V2 first? Like get the answer for V2 first? Okay? If I'm going to solve for V2 first, I'm actually going to solve this other equation for V1. I moved the V1 over, changed its sign. I moved the 8.85 over, changed its sign. This V1 gets substituted into this equation. 265.5 equals 30 times V2 minus 8.85 plus 55 V2. 30 V2 minus, we've done this number before. 30 times 8.85 is 265, isn't it? Yeah, because I did it over there. Plus 55 V2. Why is this coming out to 0? It's not. Yes, it is. No, it's not. I'm doing too many numbers in my head. Because 265.5 plus 265.5 is not 0. It's double whatever 265 is. 531. Plus 55 V2. That's 85 V2. So divide by 85. So V2 is 531 divided by 85. 6.2, call it 5 meters per second. So there's V2. How do I find V1? Plug it back in over here. 6.25 minus 8.85. Negative 2.6 meters per second. Check it. All right. So my V1 ended up negative. Why? It looks like it bounced off, right? It's almost half the mass of mass number 2. So I'm guessing that mass number 2 is really not gonna budge all that much, right? And so although V2 ended up being bigger, didn't it? So V1 didn't bounce off all that much. It's kind of interesting. I'd have to go double check that. But I do like the signs. Like V1, no, V1 had the bigger impulse. It went from 8.85 to negative 2.6, so it had the bigger impulse. Oh, that makes sense. All right, so I like the negative sign. The relative sizes of the velocities also make sense because of the impulse calculation I just did very quickly in my head. So unless there's a major mathematical mistake, which I'd have to go back and check, which I'm not going to do right now, this should be correct. This is the danger of just making up numbers on the fly. I can never check them. Not that me checking them makes any difference. I usually make mistakes anyway. That would be that'd be the hardest kind of elastic collision I would give you. Like something where you had to do the sandwich and the elastic collision.
So elastic's the one that we're doing are both inelastic and elastic both.
It's one or the other. I'm not telling you which one it is.
No, I'm saying but for both is the same way. Is that what you're saying?
You always use the sandwich, approach. It's just that when it's an elastic collision, you have an extra equation to help you figure out what's going on. In elastic collisions, typically we don't know what the speeds are of both things afterwards. In inelastic, it's either stuck together or we know something about one of the objects. What else? Torque. Yeah, do we have time to do a torque problem? We have time. It'll take the rest of the time. None of your problems had ladders in them, right? Good. Okay. Good. That is correct. I often get confused between 4A and 2A, and so I have to make sure sometimes. Because I could lay down a really hard problem right now if I do this wrong. Let's do okay. This one's probably harder than what I would give you. Do you guys know what a scaffold is? Scaffold is a structure. Technically, it's the board that like painters or window washers are standing on. Like they erect this structure next to a building so they can work on a part of the exterior of the building. The scaffolding is all the stuff, and the scaffold is the thing they're standing on, right? So they tend to look like they're all these like bars, and then they'll put pieces of wood at various levels, and then the people will stand, right? So that's what a scaffold is. This particular scaffold or piece of wood or platform that somebody is standing on is being held up by these two ropes. And the ropes are not straight up and down. They're forming angles between these things. And we have a person, standing on this structure, okay? And we don't know where this person is standing. We are given, we are told, we're not going to do the numbers, because I won't be able to make them up correctly. We're told the angles and the tensions and the mass of the scaffolding and the mass of the person. So we know the person's weight, we know the scaffold's weight. The only thing we don't know is where that person can stand so that these tensions are what we've been told. So like we're solving for the position of where the person needs to stand on the scaffold in order for the tensions to be what they are at those angles for all the other weights in the problem. So we're going for X here, right? That's what we want, okay? Okay, so how do we set this up? That's the situation. What's our approach? We need free body diagrams, we need axes, we need to be able to write down some of the torques, we need to be able to write down some of the forces. So let's tackle Newton's second law first. Okay? What are we going to call positive X and positive Y? Seeing that we're about to do 0 equals sum of the forces and there's no acceleration, doesn't really matter what we do with our axis, so we might as well pick one that looks familiar. In the X direction. Okay, so do I need to go find components of anything? What do I need to find components of? The tensions. T1X, T2, T1Y. And then T2X and T2Y. Did I get that right? Yes. Because T1 points up and to the right, so it's going to have those components, an upwards component and a rightward component. T2 points up and to the left, so it needs to have an upwards and a to the left component. All right. Anything else need components found? Nope. So check me. Tell me if I am correct or not. Oh, good. Good. T1 should be positive. Okay. Is that my only mistake? T1 needs to be what? Positive? Why? Because it points up, not down, right? MSG needs to be negative. That one needs an eraser. Are we good now? Okay. Students are sometimes upset at the speed at which I hand out negative 2s. How quickly does it take me to realize that you've made a physics mistake? Not because I'm good, not because I'm smart, because all I need to do is look at a sign, right? There could be thousands of pages of mathematics after this, right? And I know it's all gone wrong in the first 2 lines, right? Okay? It's just kind of, it feels almost unfair, right? It could all go wrong right there at the beginning, and you want to just practice. You guys did a good job identifying the things that were wrong there. Okay? All right, let's do the torque equation. To be able to write down the torque equation, what do we need? We need an axis, don't we? So where are we going to put our axis? Where the person is standing, no. It can be done. In the center, no. All of these will work. All of them will work, but only one of them will get you the answer in the shortest amount of math possible. It's right here. And how do I know it's right there? It's where X is being measured from. Do you see that? The distance X is being measured from the left-hand side. So if I'm going to go solve, did X show up in any of these equations up here? Did that distance show up anywhere? No. Okay. I might need these to figure something else out, but it didn't help me, right? So I want to put normally where would you put the axis? The point of greatest number of unknowns. But we know tension 2. We know tension 1, right? We know those angles. We know the masses. There's tons of stuff we know in this problem, right? So then we have to get a little bit more creative about where we're going to pick. I'm going to pick where the person's position is being measured from, like a kind of a natural point of reference. All these other places that you guys said, the middle, yeah, we could do the middle, and then when we solve for the distance, we'll get the distance from this, like right here, right? And then what do we need to do? We need to like change, right? We need to do some subtraction or something to figure it out. If we did it from this end, again, we would find this distance, but then we'd have to convert into the reference point that the problem originally had. So I'm just going to choose the reference point that the problem is kind of delivered to me already. So I'm going to put my axis there. So 0 equals. All right. What's the torque from T2y? 0. Why? 0 distance. What's the torque from T2x? 0. Why? 0 distance. Okay. That's all taken care of. The next force, MBG. Does it cause a torque? Yep. Torque from MBG. Is there a torque from MSG? And is there a torque from T1y? Is there a torque from T1x? No. Why is there no torque from T1x? It's pulling directly away from the axis of rotation. There's no perpendicularness to T1x, right? For a torque to happen, the distance from the axis to where the force is acting has to be perpendicular to the force. Those are parallel, there will be no torque. So those are the only 3 things that are causing torque. We didn't say which way was positive, clockwise or counterclockwise? Counterclockwise is positive. So MBG, positive or negative? MSG and T1y. You did that pretty fast, which I'm impressed with. You can also use your pencil, right? MBG causes the scaffold to rotate clockwise. MSG clockwise. T1y counterclockwise. Right? On the exam, try to keep your pencil to yourself. You don't need to like super hide it, but don't hold it in front of the next person. All right. Now, okay, so what are these torques? What's the torque for the person? Negative. The negative sign just comes down, right? And then the distance is x, and then the force is the mass of the person times g. Yeah?
Not to go back, but so you saying that the counterclockwise is going to be positive, did you just kind of say that and then we're going to follow that?
Yeah, that's exactly right. I didn't say it. Several voices in the room said it. So we'll blame them. It's their fault. Doesn't matter, actually, as long as you're consistent. What's the distance to MSG?
X. No.
It's like half the length of this thing, whatever. So the length is also given. This is how you develop test questions and homework questions too. You just start throwing something down, and then you like figure out what you know, what you don't know, what you got to give them, that sort of stuff. MS, mass of the scaffold, times G. And then what's the distance to T1y? The whole length, and the force is T1y. Okay, if we take a look at this green equation right here, do we know MPG? Yeah. Do we know L over 2 MSG? Yes. Do we know L T1y? Yes. Because we were given all the information to find it, right? So the only thing we needed was x, which means we actually don't need anything in blue to solve this problem. All we needed was the torque equation to solve for that unknown thing. We would, of course, have to go find out what T1y is, which is going to be T1 sine theta, right? Do some algebra, plug some numbers in, and we've got it. So sometimes, like, I can make a problem shorter by doing something like this, where really it's only the torque equation that you need to know, right? If you had picked an axis anywhere else than the one that I gave you, you might have needed one of the blue ones. It depends on where you pick your axis. But picking the axis there did make that a little bit simpler. Did it in less than 12 minutes. Well, I was also making it up and explaining it as I went, right? I've had faculty and students ask me, Mr. Balogh, why do you write it down every time? Have you noticed that? I start with a blank screen and I write it out, and I have terrible handwriting. I could get this all typed into the computer, right? And then just put it on the screen and talk about it, right? The reason I used to do that, used to have it all on PowerPoints and all that kind of stuff, I went way too fast. It's all there on the screen. Let's keep going, right? Okay. So this is my way of forcing me to slow down, right? So that you guys have even the remotest hope and possibility of keeping up. Not because I'm smart, but just because I've done it a lot, right? It's second nature to me because this is my job, but I keep blank screens there on purpose to force me to write it down every single time so that I go slow enough. I can teach the whole course in 3 weeks. No problem. There would be nobody passing it, but I could teach it. Well, yeah, that's really easy. Like I know how to get 100% retention and 100% success rates. It's really easy. I just give everybody A's. The administration comes to me, you need to increase your success and retention rates. Okay, great, they're both 100% starting tomorrow. That's not what we meant. That's what you said. But you got to do it ethically. Well, yeah. But you just said I had to increase them. The current success and retention rates are the best I can possibly do and remain ethically true to the learning process. We need to make physics easier. Don't you think that's what I've dedicated my career to? These are the kind of questions that happen behind the scenes. Did you guys get the email about my evaluation? No. Okay, good. So check your student emails, right? Get that evaluation link. Please, 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 please tell me how bad a job I'm doing or how good a job I'm doing or whatever. Like my favorite part of the entire evaluation process is reading your comments. They really are fun for me to read, good and bad. One of my very first student comments was, all pants must be worn with a belt. I remember that one. That one just sticks in there. And I was like, I used to wear jeans, Levi's, 501s. You don't wear belts with Levi 501s. You just don't. Anybody that does is stupid. Anyway, but yeah. So I love your comments. I have no way of knowing who it is. I don't see the comments until after the end of the semester. So you can feel free to write whatever you want. Tell me how much you hate my guts, whatever, okay? They really are the best, most interesting, and most useful part of my evaluation process. Miss B, who came and visited the class, we've had a great discussion, right? Got some insights, that kind of stuff. That's fun too, but like hearing it from you guys, that's what I really, really enjoy. And unfortunately, they only let me do it once every 3 years. I've asked if I can have these done every semester. They're like, no. Yeah, Canvas actually makes it pretty hard to truly keep you anonymous. So, what's that? I can read your handwriting. Yeah. So, so what I want to be able to do is to give people extra credit. Like I want to be able to track who's done it, who hasn't, so I can track you down at home at night and stand outside your window and say, do it, do it, do it, do it, right? I want to be able to bother people to do it. Like in my mind, the evaluation should be required and I should be giving you like extra credit for doing it. Unfortunately, the campus has made it so they can't give you extra credit. So you can ignore everything I just said and ignore and not type anything, but please don't do that. I really want to know. But I'd love to be able to give extra credit for doing it and all that kind of stuff. And it's just, it gets really dicey with me knowing like who you are, what's done what, and so. The system the schools come up with for the evaluations is not great, but it's okay. I've asked the sysadmin, can you give me a list of people that have done it? And they're like, no. So, yeah.
Why does he be so anonymous?
I did a lot of work in graduate school about how to ask questions of people, like, because I was studying how people learn physics. And the very nature of asking a question can taint a person's response. And one of the biggest taints that you can put on a person's response is whether or not they know that the person asking is going to know who answered. I said that complicatedly, but you get the idea, right? If you knew that I was going to be reading your response, you'd be like, oh, Mr. Balogh's the best. I want the truth. I don't want what you think I want to hear. And so being anonymous, being guaranteed. Now, if you put some inside joke that only you and I know, I'm going to know who it is. And people do that all the time, right? They give some comment and they're like, wink, wink, it's me, Mr. Balogh, right? Okay, but like, don't do that either. Okay, unless you want to. You can have fun with it. Other questions about physics, things that I can help you with here.
What was the formula for the equation for the something of mass?
Center of mass?
Center of mass, yes.
The position of the center of mass is, I always write it with the sum first. But it's m1x1 plus m2x2 plus m3x3 plus ... That was bad. Oh, wow. I don't know. I said it. It was in my brain correctly, and then my hand did something else. m3x3 plus ... That was like full-on dyslexia right there. Okay. Yeah, what is the ... As many as you need. So what would the next one be? M4x4. No, it's center of mass. The position of the center of mass. The horizontal x coordinate of the center of mass. And you won't need to do any other dimensions, right? It's just the one dimension. And you guys have that lab, right? Good. Yeah, because I haven't been collecting them this semester. I've been checking them, but not collecting them. No. I've already given you, I gave you the grade, right? That's the problem with this method, is I sometimes forget to post the grades. I'm good at some things. I'm not good at other things. Strengths and weaknesses. Oh yeah, I've got to write down all my strengths and weaknesses for my own self-evaluation. Should I make AI do it? One year, one evaluation, I wanted to see if anybody read them, like my own like self-evaluation. So I put some Easter eggs in there. Nobody mentioned them. I put things in there like self-evaluation. I said something like, my plans for taking over the world have been frustrated, but I've indoctrinated enough students now that I think I can put my plan into action next year. Nobody questioned it. Which either means they're on my side or nobody read it. So, plan for world domination continues. Everyone will be allowed to wear sweats.
I stand behind that.
Yes. For every occasion. Funerals, weddings.
Is there any way we can get better at the conceptual?
Yeah, this is okay. So this is a good question, and the answer is sort of. What was the hack for this class that I told you at the beginning of the semester?
Last question.
Read the book. It's like right. That's the secret life hack for this class. Read the book. Practicing conceptual questions. You can do that at the end of the chapter. I gave you homework questions. Like some of your homework questions are those conceptual ones, right? And it's so easy with unlimited attempts and only 4 choices, right, to eventually get it. You can't let it slip by. It's not good enough to get green. You have to know why it went green, right? So the answer to your question is it comes from within. Do you have the control, right, to try those questions, get frustrated, and then go figure it out before you let Wiley Plus tell you that it's correct or before you ask the AI to do it? AI systems don't do very good conceptual questions. They just don't. They kind of get stuck in certain things. So the end of the chapter in your book, at the end of every chapter, there's more conceptual questions. So they're not, I picked kind of the best ones, but you can try more of the type to try and help you. That's really kind of the best practice you can get. Griffin? Yeah. So just go to the end of the chapter. It's right after the summary. And there's conceptual questions there. I used to give 6 conceptual and 2 homework style problems on an exam. And the homework style problems were pretty long. That's when I gave a 2-hour exam. So.
Would you get a higher percentage score for the average?
No. Conceptual questions wreck students. In general, you guys would much rather crank math than have to actually know what the physics is. I don't blame you for that. You've been trained your entire school career to crank math. It's what you're used to. In case you weren't aware of it, some people are kind of getting surprised by this. I am not teaching Physics 2B next semester. Okay, I'm teaching Physics 4 series next year. I change every other year. So next year I'll be doing the 4 series for both the fall and the spring, and then the year after that I'll do you back to the 2 series, assuming nothing happens to our faculty or something like that, right? So that's the current plan. I apologize. I'm going to miss you. I will be here, right? I'll be in Grasp. I might even remember your name. It'll be a whole summer have gone by, and I'll be memorizing the Physics 4 students' names, right? Okay, so you might have to remind me. But I'll be there. If you're taking 2B with any of our other teachers, you are in good hands. You can come cry on my shoulder in Grasp because 2B is hard. How many of you have to take 2B? Yeah, okay. So get her done. Don't wait. Do not wait for me. Oh my gosh. Do not wait for me. You cannot wait a year and then come back to it, okay? The summer's bad enough. Get on with your lives. Seriously. Get on with your lives. All right. See you tomorrow for lab, moment of inertia. Give me a second, Kevin.